So just like convex mirrors, you have convex lenses, and also you have concave lenses. Okay, but if you remember, in lenses, in mirrors, convex, so in mirrors, convex mirrors were what? They were, anyone who remembers? They were diverging, right? They were diverging mirrors. And concave mirrors were converging mirrors. But here when you look at this, convex lenses are converging and concave lenses are diverging. So can you see that they are kind of opposite? But this for converging mirrors, your F was positive, right? For diverging mirrors, your F was negative. So here the sign of F for converging and diverging still is the same. If it's a converging thing, your sign of F is positive. If it's diverging, your sign of F is negative. So that stays a constant. So what you really have to figure out is whether your lens is converging or diverging. Okay. So the only thing which is changed or opposite from mirrors is this part. So in lenses, your convex lens is the converging one. Okay, so make sure you get that part correct. So sometimes in problems, they will definitely tell you it is a converging lens. So it is easy, right? Then you know it's plus. Sometimes they will just tell you it's a convex lens. So if that's the case, you should know convex lens means it's a converging lens and F is plus. Okay, so this is the F is done. And the other important thing is D naught. D naught is the object distance. And in lenses, one of the most important thing is to figure out the direction light comes. So if I have the object or something here, light is coming this way, right? So light is coming this way and it will be refracted. So lenses is based on refraction. So light rays will be refracted through the lens. And so this is the direction of the light. So I got a question again. In a mirror, convex is diverging. So yes. So in a mirror, convex is diverging. In a mirror, concave is converging. It's correct, right? So this is a concave one. So when concave, this is a concave. So in concave lenses, you remember these rays were like coming, converging. So concave was converging. Okay. That's a mirror. Okay. So I will slowly go through this. So the first thing, important thing is figuring out the direction the light rays are coming. Okay. So that is like one of the most important things when you go to lenses which have like combinations of lenses. So when there, if you have seen the lecture, there are lenses with combinations of lenses, right? So we are going to do those today. So in those stuff, this figuring out this is very important. You will see why. Okay. So if your object, usually mostly objects are real. Real means your object is in the direction light rays are coming. See, light rays are coming from this side. So if your object is in that side, it is positive. So that is what I have meant by in front of the lens. So it is really side light is coming from. So if your object is in the side light is coming from, it is a positive distance. So this is plus. So most of the time your objects, if you have one single lens, in simple problems, most of the time your objects will be real, like this. So in combinations of lenses, sometimes you will see that light is coming from this side, but your object is somewhere here. They are virtual objects. So you will see that when we go to combinations of lenses. Okay, so this is not very common unless it's a combination. We will do problems like this. If that's the case, your D naught will be negative. D naught will be negative if this object is in the opposite side to this side which the light comes from. So this is the side which light comes from. If your object is here in this side, then it will be a negative D naught. So in single lens problems, you even don't have to worry about this. So this thing comes into the picture when only in combinations. Okay. So the other important thing is this. So this is the thing which is completely opposite from mirrors. Okay, DI, the image distance. This is completely opposite from mirrors. Let's see why. So like I said before, lenses is based on refraction, right? Refraction is light going from this side and it goes from the lens to this side, right? It really goes from this side to this side. So that is refraction. So if refraction actually occurs and it makes an image, it should make the image in this side, right? If light actually goes to this side, that means this side is the positive side for DI. Because light should really go to this side for refraction to occur, right? So if it actually makes an image in this side, that means if your DI is in this side of the lens, that means your DI is positive. It's a real image. So here I have used the word behind the lens. In other words, it is the opposite side to the side where light is coming from. Okay. If you had a, let's say this lens produced an image right here. What does that mean? That means light has gone and it has refracted, but when we look from this side, it looks like the image is inside it. So now this is a virtual image. So if your DI is in this side, okay, if your DI is in this side in front of the lens, then it will be a negative value. Okay, so this is the part which is completely opposite from mirrors. So in mirrors, if your DI was here, it was a real image, right? Remember? So are you okay with this? If you know these three things, you can answer any problem in lenses. Okay. So I will move to the next slide. So you all know the sign convention now. Isn't this going? Okay. So you all know the sign convention now, and okay, let me go back. I got a question in the chat. So here I just marked DI. So this is the place. So the place is the important thing. Okay. So I really don't know what sort of image this will make unless I calculate it. But if the image is in this side, then it is negative. DI is negative. If your image is in this side, then DI is positive. That's what I wanted to tell. So if you look at here, see, DI, this side is negative distance, this side is positive distance for both convex and concave lenses. Okay. So everything else, these equations, this one and this one, you can use similar to mirrors. So let's kind of go through whether you can remember this. So if M is a positive value, what does that mean? M is magnification. So if M is positive, that means your image is upright. Okay. Or in other words, same as your object. So if your object was like this, image will be also like that. That is what positive means. And if M is negative, that means your object is an inverted, image is an inverted image. That means if your, what's wrong with this? So if your object was like this, your image will be upside down. So that is the positivity and negativity of M is. So these things were exactly same as mirrors. So M, if the magnitude of M is greater than 1, that means your image is larger than the object. Okay. And if M is smaller than 1, that means your image is smaller than the object. So from M, what you really can figure out is whether your whether your image is upright or inverted, or the size of it, whether it's large or small. So how do you find whether your image is virtual or real? Using DI. Okay. So if your DI was a positive value, that means if this is your lens and if this is your object, if your image was let's say here, so if DI is positive, so this is a case where DI is positive, right? Then it is a real image. If your DI is negative, that means if your DI was in this side, then it is a virtual image. Okay. And here I have written a small summary where you need to check for all of this information. So in textbook, chapter 23.8, if you have the textbook, it's page 665, last paragraph. They have a summary. Okay. They have a summary, and also they have all the things that I told in the previous slide. They have the sign convention as well. Okay. And this is an interesting and very important thing that you have to kind of remember, just like in mirrors. If you remember in mirrors, we like remember tiny small details, right? Which made it easier to do problems. So in the same way, here in lenses, diverging lenses always produce virtual and upright images if your object is a real one. Okay, that means if it's a single lens problem, you will always get virtual and upright images for diverging lenses. And for converging lenses, you can get all sort of things. All sort of things means you can either get a combination of real and inverted, or you can get virtual and upright images. So you can get real and virtual. So if it's real, it will be inverted. If it's virtual, it will be upright. Depending on the distance. So it will depend on the location of your object. So try to do these two and tell me the answers you get. And be very careful with signs. Okay, so always refer to the table above and do it. Okay, let's first do this one. I think the answer is correct. For this one, I have got B. Maybe I got it wrong somewhere. Let's see. Okay. An object is 12 centimeters in front of the lens. So it is a converging lens, means your F is positive, right? And F is 4 centimeters. Object is in front of the lens. That means your D naught is also positive, right? If it's in front, positive. Usually single lens cases are like this. So what we need to do is we just have to use this equation. Di plus D naught is equal to 1 over F. So Di is given by 1 over F minus 1 over D naught. And you take the inverse of it. F is 4. D naught is 12. And when you take the inverse, you get plus 6 centimeters. So what does plus means? Plus means your image is real. If it's a real image, it should be behind the mirror, right? Sorry, behind the lens, right? See? So if it's plus, it is behind the lens or in the opposite direction to the light. So your answer is 6 and behind the lens. Okay. So the next one, an image is 4 millimeters in front of a converging lens. Again converging, F is positive and it is 5. An image is 4 millimeters in front of a converging lens. So they have given Di and they are saying it is in front of the lens. So what is Di? It is negative, right? See, Di, they are talking about the image, not the object. And also they are saying it is in front of the lens. So in front means what? In front means, so this is lens. In front of, in front means it's negative. Oh, sorry, Di. Okay. It's image, okay. So we can use the equation just like before. D naught is 1 over F minus 1 over Di, Di inverse 1. Now we just have to plug the values. F is 5 minus Di is also negative, right? Oops, what did I write? Negative 4. So negative negative becomes positive. So what you really have to do is you have to add 1 over 5 plus 1 over 4 inverse 1. So what do you get when you do that? 1 divided by 5 plus 1 divided by 4 minus 1. So 2.22, right? Did you get the same thing? So I got plus 2.22. So this is D naught. D naught positive means it is in front of the lens. So 2.22 in front of the lens A. So are you okay with these two? Yes? Okay. Oops. I have given you the answers in this. It's okay. So do these two and tell me once you are done. Okay. So you all have done it. I got 5 tons. Okay, 7 tons. So when an object is 40 meters in front of a converging lens. So converging is again F is positive. 40 meters means in front is positive for an object. So D naught is plus 40. When it's 40 meters in front of the lens, the inverted image is half the size of the object. Inverted image. So why did they tell us it's inverted? What is the meaning of inverted? If you remember, M is a negative value if it's inverted, right? Yes, M is negative. Okay, so let's see what they are talking about. They're asking what is the focal length. So they have given us the value of M, right? In inverted image is half the size of the object. So what is the value of your M? You know, so yes, it is 0.5, right? It is half the size of the object. You all know that M is the size of the object, size of the image divided by size of the object. So what they are saying is it is half the size of the image and also half the size of the object, and also they have said it's inverted. That means your M is negative and it is 0.5. So that is what this part means. Okay. So do you get that it is negative and 0.5? Okay. So they're asking for F. So I got a question to explain it again. So do you remember that M, the value of M, if it is negative, that means what? It means it's an inverted image. And if your M is a positive value, that means it is upright. So here they are saying your image is inverted. So this is them telling us that M is negative. So this is how we figured out this negative sign, because they said it's an inverted image. Okay. And also we know the value of M tells you the size of the image divided by size of your object. So it tells you how big your image is compared to the object. Okay. So they are saying your image is half the size of the object. In other words, that means the magnification is half, right? It is 0.5. Okay. So you're okay with this now. And they're asking for f. So we know f is a positive value. That's all we know. In order to find f, we need di, right? We need di. So if we knew di, then we can use this equation to find f. So the problem is figuring out di. So we can use this magnification equation to figure it out. We know m is given by negative 0.5. And also we know m is defined as image distance, negative image distance divided by object distance. This is the equation of m, right? Okay. And object distance is 40 positive. So negative 0.5 is negative di divided by positive 40. And you can see this negative sign and this negative sign cancels. And you get the value of di as 40 times 0.5, which is 20 meters. And we got a positive value for di. See, we got a positive value. And we kind of knew it, right? Because do you remember when I initially said images are formed in like pairs? Pairs means if your image is inverted, it is real. If your image is upright, it is virtual, right? Remember? In the beginning, I said they usually come in pairs in the summary. So when they said that it's inverted, we should know that finally, when you calculate this, you should get a positive value for di. Okay. So even if you didn't know that, we get the value using the calculation. Okay, so we have di. Now we just have to plug the value to this equation. So f is given by 1 over di 20 plus 1 over d naught 40, and you take the inverse. So when you do this, you will get 13.33 meters. Again, positive value, and we know it. Converging lens should give you a positive value. So your answer is A. Oh, yeah. So it should be meters, or this should be centimeters. So problem with the question. It's a problem with this problem. Okay. So it's a mistake. They should be in the same units. Sorry about that. So they should be either in centimeters or they should be in meters. So I'll put centimeters everywhere. Okay. And I'll change it to centimeters. Okay. So are you okay with it? So when you read these problems, as you read, just write down the things that you know. For example, this thing. Then it's easier to do the problem. Okay, this one. An object is 6 centimeters tall. So what have they given us? H naught, right? Height is H. H naught is 6 centimeters. And it is in front of a diverging lens. First time we are seeing a diverging problem. Diverging lens, F is negative. And what else do we know about diverging? If you remember, what about the images? Do you remember the sort of images it makes? Very good. So divergent lenses always make upright and virtual images for real objects. So this is a real object because it is in front of the lens. Okay. So I'll just write it here. Always makes virtual and upright images. Let's see. We don't need that, but if we know that, it's easier to compare things when we get final answers. Okay. Then they are saying image is 2.5 centimeters tall. HI is 2.5 centimeters tall and 7.5 centimeters from the lens. Okay, so that is the important thing. They have given 7.5, but they haven't said where it is, right? They haven't said it is whether it's behind or in front. So here is a scenario where they test your knowledge. So you should be able to tell me whether it's positive or negative. What is DI? Like it is negative because we know diverging lenses always produce virtual and upright images. So when they said image is 7.5 centimeters from the lens, it is really in front of the lens. In other words, it is a negative value. So do you get that? Yeah. So for these problems, like you should really know what you are doing because they can easily omit things just to test your knowledge. Okay, so we have written down most of the things. They're asking for F, right? We know for F we should get a negative value because it's a diverging lens. But to get F, we need to find D naught. Yes? So let's find it. M is given by what? H naught. Hi over H naught. And also we know diverging lenses make upright images, right? That means this is a positive value. So we can just plug 2.5 for H, I and 6 for H naught, and we can leave it to be positive because we know M is positive because it's an upright image. And it is equal to minus DI divided by D naught. So that is your equation, right? So what I'm going to do is I'm going to plug the value for DI and find D naught. What is DI? DI is negative 7.5. D naught is what we need to find. So D naught will be this negative and this negative will become positive. So if you calculate this, I have got 18 centimeters. So I have the value of D naught and it is a positive value. See, we got a positive value here. Even we know that this is in front of the mirror. See, object is in front of the mirror. We know it is positive. So in front of the lens. So we know it's positive. Okay. So we know DI, we know D naught. We can easily calculate for F, right? F is 1 over D naught plus 1 over DI inverse. We have to be careful when we are substituting because DI is a negative value. D naught is 18 What is di? Di is negative 7.5, right? So this positive 7.5, this positive and this negative becomes a negative. So you have 1 over 18 minus 7.5 inverse 1. So when you do that, I have got negative 12.86. So what is the closest answer? So the closest answer to this is 13 centimeters. So 6 weeks is 2, right? So when you round it off, you get 13. So are you okay with this? This is a hard problem, testing so many things. Okay. So here is a problem where there is a combination of lenses. That means you have 2 lenses back to back. So one after the other, you have 2. Yeah, I'm asked to go back for a second. Okay, so I'll go back for a second. So tell me when you're done with this slide. Okay. So let's do this problem together. Okay, because I want to go through few important things. So I will let you do things alone, but I want to go through few things together. Okay, so there are 2 converging lenses, one after the other. Oops. Okay, one lens, and we have another lens. And the f of both the lenses is 25. Since it's converging, they are positive values. Okay. So whenever you get problems like this, you have to draw a diagram. Why? Because if you don't draw, it will be so confusing to do a problem. And they are saying lenses are placed 16.5 centimeters apart. So this distance between the two is 16.5 centimeters. Okay. An object is placed 35 centimeters in front of one lens. So what is your object? This one. So I'm going to draw your object in front of this lens. And it is 35 centimeters from the lens. Okay. So if this is your object, what you will be doing is you will be looking at this lenses from this side for your image, right? That is because what actually lenses do is they refract light. So when you are looking from this side, light is coming like this, right? This way. So this is the direction of light. Okay, so direction of light will depend on where you mark your actual real object in the beginning. Okay, so usually we like to start from here. That's the norm, right? We usually draw object in the left hand side. Okay. So here they are asking where will the final image be formed by the second lens, where will the final image be formed by the second lens be located? So what will happen? So what is happening is this light which is coming from this object will get refracted from this lens, lens number 1, and this lens will form an image somewhere. Okay, we don't know where it will form the image, but it will form the image somewhere. Let's first find it. Okay, let's first find di of the first lens. So do it and tell me what you get. So this is your d naught. It is positive. You are going to use this d naught and this lens and tell me what you get for di. So I got one answer. I will wait for more. Yes, your answer seems to be correct. I'll also do it. So you can keep on giving me answers, okay? Yes, so 87.5 is what you have got. I will also do it. So from the first lens, F is, sorry, not F, I'm mad. So your 1 over F is 1 over D naught plus 1 over Di. We need to find Di. Di is 1 over F minus 1 over D naught inverse. So when we plug the values, F is positive 25. D naught is also positive, it is 35. And when you take the inverse, what do you get? You get plus 87.5. So if you have got a negative sign here, that means you have subtracted this from this, the other way. Okay, so be careful when you rearrange the equations. So you get plus positive image. So where is your image? So it will be 87.5 centimeters to the right hand side from this lens, right? So where is the image? It's far away, right? It is somewhere here. So we know the place, but we don't know whether it's upright or inverted. We really know it, but let's assume that we don't know. We know usually when we get a real image, it is virtual, right? Sorry, it is inverted, right? So let's calculate M. So can you calculate the magnification and tell me? This is the equation. So 2.5. Is it positive or negative? Yes, negative 2.5, right? Negative di is positive 87.5. D naught is 35. So when you do calculate this, you get negative 2.5. That means you get a image right here which is inverted. So that is the image made from the first lens, right? So this is the image from first lens. So what is really happening is light is coming, okay, and it goes this way to make a image here. So light is still coming from this side, right? Although it made the image here, still light is coming from this side. Okay. And the image formed by your first lens is the object to your second lens. That is the most important thing. So I will use a different color for the other mirror, other lens. So this is the image from the first lens and object to the second lens. Okay. So what can you tell about the second lens now? So light, the direction of light is this way, right? So direction of light is like this, still this way. Here is your lens. This is the second lens. And your object is now here. Okay, object is now here. So what can you tell about D naught? Is it positive or negative? So for the second lens, this is second lens. So D naught is negative. The reason is light is coming from this side, right? Light is coming from your left hand side, but the object is behind the mirror, behind the lens. So this is a virtual object for this lens. It is negative and we need to find this distance now. So let's see what's the distance is. So this whole distance is 87.5, right? So this whole distance is 87.5. So what should be this distance? It is 87.5 minus 16.5, right? This distance minus the distance between the two lenses. So when you do that, you get 71 centimeters. Yes, you have got 71 centimeters. So this is 71. So my suggestion is first draw this big diagram, and once you mark this, it might be very confusing. So then draw another tiny diagram for the second lens. Okay, then you can see see things very clearly. So this is a virtual object for this mirror, this lens. So di is negative 71. We know f is positive 25. They have given in the question. So we can find di for this, right? So can you find di for this and tell me what you get? So you have got answers. So I'll wait a little bit till 5 of you tell me the answers. Okay, so I'm getting so many answers. I will do it quickly. F is 25 and D naught is negative 71, right? Negative 71. So when you this negative and this negative will become positive. So you basically have to add 1 over 25 to 1 over 71 and take the inverse. So when you do that, you get 18.49. That means 18.5 centimeters positive. That means where is your image? In this side, right? In somewhere here. Somewhere like 18.5 centimeters from the lens. But we don't know whether it's in which direction it is. So let's see. Can you calculate M? You get positive to 0.26. That means if your image will look same as your object. So here your object is like this, right? It is like this. Your image will also look like this. Okay, but this is not your final answer. Your one part of your final answer is done. You know the final image, where your final image is. But we still don't know the final magnification. We just found the magnifications of each separately, right? So we figured out the first lens magnifies it by this much, and the second lens makes it smaller by this much. So when you have a combination of lenses, the magnification, the total magnification is given by the multiplication of all the lenses. Let's say you have a mirror also, then you can keep on multiplying all of this. Let's say you have 10 lenses, you will multiply the magnification of all 10 lenses. Okay, so you have 2 lenses here. So from the first one, you got negative 2.5. From the second lens, you got plus 2.6, 0.26. So when you multiply the two, you get negative 0.65. That means your final image is still inverted. So we knew it, right? We knew it was inverted. And it is, we know it is 18.5 centimeters away from the second lens. And it is 0.65 times your original real object you had initially. So it is 0.65 of this original object. Okay. So are you okay with this problem? So this is a simple case of two lenses together. Are you okay? So tell me when you are done with this. I will move to the next slide. A small object is 25 centimeters from a diverging lens as shown below. Okay, so this is the object and it is real, right? A converging lens with focal length 12, okay, is 30 centimeters to the right of the diverging lens. So this length is 30 and the focal length of this lens is plus 12 because we know converging plus. The two lens system forms a real inverted image 17 centimeters to the right of the converging lens. So they have given the DI of the second lens, right? They have given the final image length, distance. So they have given for the second lens, these are the things that they have given. They say that f is plus 12, di is plus 17. So they have given these two. So can we find d naught for the second image? Yes, right? So if we can find d naught for the second image, we know that is same as the image from this, right? Okay. So let's first find d naught for the second lens. Second lens means the converging one, this one. Also, can you find maybe m, just to see what has happened? So you have got negative 0.417. So it is not needed for the problem. I just did it. Okay. So we found the location of d naught. So here I got the value for d naught as positive 40.8. That means your object is somewhere here, and also you can see the magnification we get is negative. That means the object was upright image for this one. So if you have upright one only, you get a inverted one, right? See, negative means that, right? And this d naught is positive and it is 40.8. Okay. So we found main things for that. Now we have to mark this in the main diagram. So where is this? 40.8. 40.8 is somewhere here, right? is somewhere here. This is the object of the second lens, and also it should be the image formed by the first lens, right? Image of this lens, image of the diverging lens. We know the image formed by the diverging lens, this one is the object to the second lens. We did it, we learned about it in the previous problem. Okay, so what I'm going to do here is I'm going to draw a separate diagram for this lens. For this lens, this was the object. Object is 25 centimeters away. They have given it in the problem, and we just found out and that this is the image, and it is so what is the distance? What should be this distance? 10.8, right? Because this whole length is 40.8, and you have the diverging lens here at 30. So at 30 you have the diverging lens. Therefore this part should be 40.8 minus 30. So this part is 40.8 minus 30, which is 10.8. 10.8. And what can you tell about it? Is it a negative or a positive value? Looking at the image. So DI is negative, right? But compared to this lens, it is in the side where the light comes from. In other words, it's in front of the lens. So we can use our equation, this equation, to find the focal length. D naught is 25 and DI is negative 10.8. So that means here what you have is a negative value. Negative times positive becomes negative. And when you calculate it, you get negative 19 centimeters. And we know for a diverging lens, f should be a negative value, right? So we got a negative value, which means it might be correct. So it is like a check. We get a negative value for the diverging lens. So are you okay with, let me know when you are okay with this, okay? So that is what they're asking, right? What is the focal length of the diverging lens? So always solve one lens at a time. Okay, solve one and then go to the other. So here, a thin converging lens have a focal length of 70 centimeters. So therefore this is 70, and a diverging mirror of 40 centimeters. So if it's a diverging, the diverging word means it's a negative value. So f is negative for this mirror. So the important thing here is, for the lenses, you will have to use conventions, sign conventions for lenses, and for the mirror, you are going to use sign conventions for the mirror. So they are separated by this distance, and the object is here, and they want us to find the final image. So for the first step, so this is your lens. So initially you have this object, which is 100 centimeters away. So D naught is plus 100, and your F is also plus 70. So this is a very nice one. I want you to calculate DI and tell me. So calculate DI, it's easy, right? It's a simple one. And also calculate M and tell me what you get. And like I said at the beginning, always when you have a real image at the start, that's where the light is coming from. At the start. We will see if it changes later. So this is light. So I got one answer. Can I have more for DI? Okay, so if I calculate DI is 1 over F minus 1 over D naught, and we need to take the inverse. F is 70, this is 100, and when you take the inverse, you get 233.3 centimeters, which is plus, right? That means where is your image? So image is behind, in the opposite direction. So it's here. It is 233.3 centimeters away, and let's quickly find the magnification. M1 is given by minus DI 233.3 divided by D naught. So you get a inverted image here, right? So light goes from here, and if we didn't consider this mirror, what would have actually happened is it would really converge here, but right now it looks like it's converging here. Okay. So that is what happened. Still light is going this way, right? So next what happened? What will happen? So now light is coming towards the mirror. Still light is coming this way, right? Light is coming towards the mirror, and this image made by the lens, so image by lens, is the object to the mirror, right? So this is the object to the mirror, and mirror will produce an image for this object. So what I'm going to do is I'm going to draw a separate diagram for the mirror. So this is my mirror, and the object is somewhere here. This is the light, direction of light. Light is coming from this side, right? Still it's this way. So this is D naught. What can you tell about D naught? What is that value? So this is 100. This whole thing is 233.3. Therefore, this distance should be 133.3, right? So D naught is 133. I want you to tell me whether it's positive or negative. What should it be? Negative, right? It is negative because we know object distance, whether it's a mirror or a lens, if it's opposite to the direction of light, or in other words, behind the surface that we are interested in, it is a negative value. Okay, so D naught is negative 133, and your focal length is also negative 40 centimeters. So I want you to use the mirror equation, so the same equation that we use for the lens, and tell me the value of di for the mirror. So when you do this, and you see there are two negatives. These two negatives will become positive, and here you have a negative. So you will get negative 57.148. And for the magnification, I will write it here, M2. For the magnification, you will get negative di over d naught. Di is negative 57. D naught is also negative 133. So negative negative becomes positive, and again you have a negative, so magnification is negative 0.4287. Okay, so we have done most of the problem, but it is not completely done. So this is the interesting part. There's another part for this problem. Let's see why. So first let's mark the image. So it is negative 57. So for a mirror, what is negative? What does negative means? For a mirror, is it behind the mirror or in front of the mirror? For a mirror, you remember it. What does negative mean for a mirror? So I got the answer. Yes, it is behind the mirror. So for a mirror, negative means behind the mirror. So it is negative 57. That means 57.15 centimeters from the mirror. That means here, and also your magnification is negative. That means what I have marked is wrong. Magnification negative means this was the image, this was the object, right? It should be upside down of your object. So if it was like this, your image will be like this. Okay. So this is not the end of this problem. Why? Because this thing is a mirror, not a lens. If it was a lens, light will go and leave the mirror, leave the lens and go that way. Keep on going. But when it's a mirror, what will happen? What does a mirror do? Mirror will create this image here, but what it actually does is it reflects light, right? So it seems like it's creating an image here, but what it actually does, it reflects light. So this reflected light from the mirror will now go again and hit this lens, and again something will happen, another refraction. So that is the difference when you have mirrors. Okay, so I'm going to draw it. So here, so refracted rays are now coming back from the mirror. So if I draw it, so here is your image object now. So this is your object, this one, this thing that we found before. It is at 57.15 from the mirror. So what can you tell about the distance from the lens? So this was your mirror. This was 57.15, and this distance between the lens and the mirror was 100, right? So your D naught is 157.15. Okay, now this is the interesting thing. Look carefully what I'm going to mark. So which way is the light? So light is now refracted, right? Light is coming this way now. So now the direction of light is this way. Is that clear? Because light is refracted, right? Sorry, reflected. What a mirror does is it reflects light. So the light which initially came from this side is now reflected from the mirror. So now the direction of your light is this. So this is a scenario where this direction of light becomes important. So now can you tell me what your D naught is, whether it's a positive value or a negative value? For a lens, we know the light, if the object is in the direction of light, it is positive, right? That is how I initially defined the table. So this value is positive because light is now coming in the other way. So this is a very special case which will only happen when there are mirrors in combination. Okay. So this is your D naught, and everything else is very similar. What is F? F is, they have given 70. So can you calculate DI for this? So I got an answer. This is 70, this is 157.15. So when I do this, I get 120 something. So I have got 128. So I will write it like that. Maybe, oh, no. I think you all are correct. So 126. Okay. You get 126.2 centimeters, and it is positive. So looking at this diagram, can you tell me where should DI be? Positive means which direction? For DI, positive is this way, right? It is opposite direction to the light, opposite side to the light. So your DI will be somewhere in this side. So if we calculate M, so I'll write M3. M3 will be DI over D naught plus, oops. So when you calculate, put these values, DI is 126.2 and D naught is 157.15. So what do you get when you put those two values? Negative 0.8. So I don't have room, that's why I just wrote it like this. So you get negative 0.8. And that means your image is inverted again compared to the object. So it is here 126.2 centimeters from the first lens, and it is upside down. And now we can calculate the total magnification, right? We know the total magnification is M1 times M2 times M3. So three things happened here. One, image was formed by the lens, then that image was used by the mirror to form an image again, and the mirror's image was again used by the lens to make an image. So three things are happening here. So we just multiply the three M's. Negative 2.33, negative 0.4287, and again negative 0.8. So when you multiply these three things together, you will get 0.8. So even for this one, you should get 0.8. Okay, so that means you get a smaller image.